first part of today is advanced segmentation. So we have already looked at different ways to do segmentation, mainly just based on looking at the histogram and possibly also looking further on how we can set thresholds manually. But that is not a good approach, in particular if you want to do it reproducible, and also not if you want to have it. Let's see if this one works. No. There it is. So, if you want it reproducible, in particular if you want to do it over very many images, then the manual approach is not really recommended. So today we're going to talk about some motivation for how to do it more automated, particularly if we have many samples. Then of course we come to the cases where it's difficult to segment it automatically, and in some cases very hard to segment it automatically actually. Coming into a little bit about the supervised methods, how to do training, learning methods, and also some tricks to improve the segmentation performance. With this, we use different feature vectors, so we try to look at different aspects of the data using then also k-means clustering, superpixels, and so on. There is some papers or a link to material about superpixels. It's a special category of clustering that I'm going to mention in the first part now. And to run this notebook, we again have a lot of modules to load, and here we mainly, the new ones are here from scikit-learn. Is in this part the most interesting. We also have and yeah, that's more or less it. We have the morphology, we have some filtering, so that's what we know from previous lectures. And what we have done until now, we have looked at databases, which is becoming very important now for this part, and also the importance of ground truth and looking at ROC curves. And we also saw that we can have different histograms depending on how the data is looks. And now we want to go into choosing a threshold automatically. And let's see how that goes on. There are different kinds of segmentation. So you have a picture of, in this case, 5 tough bikers. And you can do object detection, so you can just put a frame around each person. You can also do semantic, let's see, where am I? Oh, I'm in the wrong place. So semantic segmentation is just say it's a person or it's a background. And you can do instance segmentation, identifying that this area is covered by person 1, 2, 3, and up to 5. That is something we're going to do in, I think, next week's lecture. Today we are mainly focusing on this part to say it is something or it is not something. And there is always cases where you can't really see or segment it pretty well, so you have to look at different aspects. And I really like this painting because you probably all really well see the fox, but do you see the Indians and do you see the ponos on this one? They're actually here. So here we have one Indian, his face, and here we have the other, and the pony is about under here. And this is really obscured, and That is also what you can come across during your analysis of your images, that everything almost look the same, but it is not the same. And that is the challenge in this case. And typical cases when we have problems is first classic one that we have some measurement artifacts. In this case, I have some ring artifacts. And when I try to segment that, I have a lot of misclassifications, both outside and inside the object. Noise is less structured than the artifacts, but it can really obscure the data. So we may have a histogram that is quite flat. There is no really information to get it, but you can actually, by the eye, you can actually see that there is something, but it's very hard to tell the computer to find it. And if you try to segment this one, putting a threshold somewhere, you will just get a snowstorm. There will not be very much to look at. Yet another one, which is quite annoying actually, is that if you have gradients in your images, for some reason it can be bad illumination, you weren't able to normalize or have some reference images to get this illumination field. And when you try to segment this, first the histogram looks quite weird. And when you try to segment it, the natural place would be here. And then you would get actually both the items and something that goes above the threshold level caused by the gradient. Then, which is a case which is also quite common to see, is that you have noise combined with the unsharpness of the images. And what is interesting to observe here, that the noise controls the width of these two. And of course, then you have the contrast, which says the position. But normally, with this noise distribution, you would get all the way down to 0 counts between the two. But thanks to the unsharpness, blurring along the edges, you have a lot of gray levels which are filling up the gap between. So the more unsharp image you have, the higher the in-between level becomes. And when you try to segment this, of course, you have a great uncertainty in this area. You get quite fuzzy edges when you try to segment it. This is an example what can happen. Just a toy example. I took the same image and added random intensity levels on the images, and each color here, color frame, has its histogram, and you can see that there is a slide in the bias of these histograms. And if we try to segment these images, all images using the same threshold, it doesn't come out very well. So right now I did a test with putting the threshold at 0.6. These images are normalized between 0 and 1. And then you can see that in one case, you have a volume fraction of these white spots, 1.5%. In the next case, where we have a very dark image, then the majority is coming out here. And then we have a completely different volume fraction, a quarter of the whole image. So that can give us a really huge differences in the outcome and also for the analysis. And it was actually very dark. And then you can see the other ones, they are fluctuating between 1.5 and 7-8%. Looks more natural, but you have to be aware that probably you need to set the threshold individually per image, so you can't rely on the fact that you can use the same threshold. So maybe you have to re-initialize the thresholding algorithm, which is bad. So in principle, you should make sure that you have everything normalized in good range before you start doing anything. One thing that I came across in the beginning when I started at tomography data that was that someone had normalized all the gray levels in each slice of a tomography scan. So each slice had different threshold levels, and it was close to impossible to get a decent segmentation of that data. So be careful when you set the threshold, when you set the gray levels of slices in a tomography. Make sure that everybody have the same interval. So where we fail, here is an example. We have this bone slice and want first to find larger cellular structures. And we also want to find small channels which connect together. So we have the large structures looking at these with a white boundary. And then we have the tiny structures are these dots that we also want to find. And the first one is quite easy. There is good contrast. But the second task is more difficult because maybe the signal to noise ratio is too low. Can also be that we don't resolve it sufficiently, so we get partial volume effects. And that makes it much harder to segment these items. And they're also small. So the question is it really the item we want? Is it maybe just an outlier in the data? They don't have that neighborhood to play with. Another one is the brain cortex, which is in this area of the image, and now it's marked out with red as the ground truth. But looking at the image, you would see that there is almost no contrast difference. There are no clear boundaries. So the question is how we can really find this area, and if it is possible at all, if the information in the image actually carries this. And we will try some different approaches to find it, but let's see what we can do. The first approach would be just to apply a different threshold, as we have done before. Just this one, I think, is uniformly distributed, just putting threshold on different gray levels. And the output is not really convincing. We can see actually in this segmentation that we have a gradient in the image, that it's brighter at the border and darker in the middle. We also get something, I don't know what that is, actually, some structure where it's put, I don't know. Or is it bone structures? Looks too well shaped to be some biological structure, but I don't know, actually. Now, these were the tricky cases, but there are many cases where we actually can do good segmentations. And one example is you can use existing tools. Here is a screenshot from ImageJ, where you have, what is this, like 15, 20 different algorithms, how to do the segmentation. And well, it's a very nice tool because you can drag a slider, you can see what happens in the image when you do it, and you get this red mask. And all these methods, they are dedicated to different problematics or different types of histogram. Some are very simple, others are more deep going in looking at entropies or cross variations, etc. And we can have very different approaches. So until now, we have looked at the histogram and ways to find, looking at the histogram shape or the statistics in the histogram in order to find our threshold. We could also look at image information. So in this case, looking at entropy in the image to find the threshold, or we can also use results-based. So say we want to find a threshold that gives us items which are in the size range of 200 till 10,000 pixels. And using that kind of algorithm is sometimes powerful, but sometimes very dangerous, because if you have misclassifications which are in the same range, they will also be classified as objects. And that can be the trouble with this. But it's a way to actually find these thresholds too. Starting out with the histogram based, looking again at these bone cells, the histogram is not really convincing to do segmentation on. We have the big gray mass, the background, which gives us a large peak. But then it's very hard to say where to put the threshold to get these large areas. Probably we should put it somewhere in this range, but it's not really clear where. The very high peak here is probably some kind of data clamping, so it should actually continue deeper down. But because of the gray levels available in the image, we couldn't get that. But anyway, there is a little bit of a rise back here, so we could actually guess that the threshold should be somewhere between 0 and 0.2. That would probably give a reasonable starting point. Then there are a lot of different methods. We can take, if you have two clear peaks, you can do the intermode. So just locate the maximum of mode 1, maximum of mode 2, and compute the average between them. That's one way of doing it. The Otso method is doing something similar, but more statistically motivated. So it's trying to optimize the statistics in a way that you minimize the variance within the class and maximize the variance between the classes. And by that, you get a cost function that nicely puts a threshold in the middle, somewhere on a reasonable place. This is a classic algorithm. It's probably the go-to method when the first one you try is to use the Otso method. And it's implemented in, I would say, any image processing package. It's quite quick to compute, and that's why it's used. Then there are isodata, which is a little bit of an iterative approach where you try to optimize the thresholds as the average between background and average of the objects. And with that, you also balance in somewhere in between the two classes. And then, as you saw in the image example, there's so many different algorithms. We can, one way of actually finding the right thresholding method is just run everybody in a loop, go through them, and in scikit-image, there is actually a very nice function for doing this. Try all thresholds, and then you just give the image and say how big the image size figure size should be, and then it prints out, shows all the results. And here you can see, I couldn't browse again. But anyway, you will see a lot of different methods that are available in scikit-image. The most of these, they are optimized to work with two peaks. Some of them, they're working towards single distribution. You have a class imbalance, and expecting the interesting part are very few pixels, and they are distributed in the tail of the distribution of the main image. Then you can use some specific methods that work pretty well on that. So, there are of course also pitfalls in using all these methods. So it depends on the histograms. really need nice separation between the classes, otherwise it will not work. The image-based, they are also sensitive to noise, and if the amount of noise is overwhelming, these methods can change the statistics and then also misguide for example, then the entropy. And as I mentioned, with the results-based, if you ask for items in the order of 200 till, now I wrote 1,000 pixels. Before it was 10,000, doesn't matter. But anyway, if you ask for objects in this range, you will find them. And it doesn't mean it has to be meaningful. So we can look at different approaches to work with it, and the first thing is that you can't expect that you are getting 100% correct. You have to accept some kind of errors. But we can test our segmentation performance and doing it based on a model. So we already talked about that in previous lectures, that we try to simulate everything as well as possible and then see how it works. And then if we can get, say, a 95% accuracy in our analysis, then it's quite good. Or you can, of course, set which accuracy you want, depending on your criteria for the data. We can also work on the samples themselves, so we can try and see what each threshold is doing, and then we can see what every case can approach. Yeah. Unfortunately, the last one, it doesn't want to appear. Yeah. Then I need to leave. Yeah. Then you can always come up with some kind of worst case scenario where you have a lot of noise, misalignment, etc., and see how bad the results can become, and then doing statistics on that. Let's go back to this one, and this is a lot of code. I kept it here because it was difficult to actually split out the part that is directly interesting, because there is a loop in the middle that puts out the data. But in principle, what we do is that we have in our image, we have some large structures which are very clear, but we also have smaller structures, and to get them, we need to set the threshold maybe a little bit deeper than we would like to, and with that we get a lot of misclassifications. So what we can do is we start segmenting in different regions, and again I actually need to let's hide the code anyway. It's better. So then it's easier to see. So we have this image, and you already saw its histogram, that it's a single mode. And the interesting parts, they are mainly on this left tail of the histogram. And now we set two different thresholds, one which is quite restrictive and one that is more generous. And looking at this image, you can see that we have now the colors green, gray, and yellow in the image, and most of the small items land in the yellow part, and the larger items land rather in the gray part. So there we already have a distinction with this, and this is something we can use now, because we can use the restrictive threshold as a seed to grow out into the less restrictive, and then we get a much better segmentation. And here we can see what the thresholds actually provide. We have one threshold which is very restrictive, so we don't get much of structures here, and one that is, well, too generous. And in principle, what we normally would do is yeah. So here is threshold 1 and 2, and in principle we would have two classes here. I tried to draw in more or less what the distributions would look like. So we have one distribution here, we have one distribution here, and of course there is an overlap, and this overlap is what's giving us the misclassifications. And you can see that the red one is more or less where the orange histogram is landing on the curve, and the green one is more or less at the end of this distribution. So these are the two boundary conditions we are playing with. And here we can play a little bit with the Goldilocks fairy tale about the little girl that comes to the bear's house and wants to try everything and finding out what is the best for her. And she comes always to some kind of middle solution. And this is more or less what we are doing here. So first we do this region, identifying the regions. One is too small, one is too big, and we want the thing in the middle. And now we can use something called region growing. So we are actually taking the restrictive and grow out until we reach the boundary of the finer, the boundary of the less restrictive. And with that, we can actually get a quite good segmentation. So we have the strict threshold, and we removed some small objects by probably opening or opening in this case. And then we have the loose threshold, which is just a forest of a lot of dots, which we don't want. And if we combine the two, we can see that there is some overlap, of course. And then we can just use the connected threshold where these are used as seeds in that one. And then we get this as final segmentation. So this is quite good approach to eliminate a lot of misclassifications out in the black, and still maintain the original structure. So this is kind of an alternative also to using the opening and closing operations that we looked at last week. Next problem comes when we are looking at multiple thresholds. And this is really, oops, that wasn't meant to happen. Let's see again. So that was what I wanted. So when we have multiple thresholds and they are actually overlapping with each other, there can be problems, what I call a virtual skin. And I have seen really bad examples of people putting interpretation in this skin. You can see it here on the boundary of this item. In principle, this should be a square that a high intensity square that touches the background. But thanks to the problem that we are going from this histogram, which is the background, over to this one in one big step, we're actually passing through also some gray levels from the. This can be seen where I look at the edge profiles. So I'm just plotting the pixel intensities in 3 positions here. So we have the blue, orange, and green. The blue goes from background all the way up to the foreground of the higher intensity. The orange one goes from the high intensity to mid intensity, and the green one goes just from mid intensity down here. The orange and the green, they are harmless. They're no problem. But the blue one is actually a problem because here we have 1 pixel, or maybe several pixels, which are in this orange region. And they will be classified as the wrong class. And that is what we want to avoid. And there, of course, yes?
What does position mean?
Position, that's the pixel position. That's the coordinate. So that's a coordinate along the x-axis. So it's really, I'm just plotting the gray level intensity as function of the x-axis. It's not an absolute value, actually, that I could have improved, but it's anyway the x-axis, position along the x-axis. So what we can do, we have this segmentation, which we're not happy with. And one approach, there are many ways to do it. One is, again, the hysteresis. And another one is using guarded edges. So what we do is we compute maybe a smooth form of the gradient of this image. Then we get the edge magnitude. And when the edge magnitude is above some threshold level, then we have a dangerous edge. So this would be the box. And this one we will leave out of the segmentation in the first run. And in the second run, we do region growing from all the other pixels, and it will approach and come to the place. And the final result is something like this instead of that. I think I did some cleaning too on this one, to be honest. Otherwise, it wouldn't have been this clean. This works. It was a quite simple code, actually. And if you look very closely, you can see that there is a little mistake in this corner here. So this is a way how you can avoid doing the misclassifications along the edges. Of course, there can be ambiguous cases where you actually also are looking for very thin layers on the surface, and then you have to be more creative and more careful about how you do it. Then we can always do everything more complicated. We can work with color images, also full spectrum images in our segmentation. And each voxel or pixel contains vector valued information. And from that, we can do also more detailed segmentation. And we can also use, oops, that was kind of lost up there. I don't know why I always, there it comes. And one thing we can look into is starting using feature vectors instead of just single images. And here we have a case where we have a really bad illumination. And segmenting this one will not give you very good results. So what we can do now is a little trick. We compute the background as the, in this case I use the median. No, Gaussian, sorry. Gaussian with a very large kernel. And the very large kernel will smooth out every little detail. And the outcome of it is actually the gradient in the image. There are different approaches doing this. In this case, it was the Gaussian. Can also use the median. There are cases using combinations of morphological operators called a top hat, which is and the bottom hat, and now I actually honestly don't remember exactly the order, but you take an open gray level morphology opening or closing and subtract that from the original image and also get something like this. And by subtracting that information from this one, you get a much better image, much more homogeneous illumination in the image, and that makes it much easier to segment. And here we can create a little feature table just to see what it looks like. We have different positions, their intensity, and our ground truth if it is text or not, and then we can make some tests and see how well this works. And first thing is to look at the histograms. The first looking at pixels that belong to the text, which are blue, and pixels that are background, they are orange here in this histogram. And you can see that there is a large overlap between these two histograms, which is unfortunate for our segmentation. With this kind of histogram, we would probably set the threshold around here, because that's the overlapping point, but that wouldn't give us really good results. And if we try to do a segmentation based on this, we see that we have an ROC curve which actually bulbs up quite well, but it's still not really convincing. So let's see what we can do about this. We could add some information, and in this case, let's try doing the difference of Gaussians. And the difference of Gaussians is essentially a high-pass filter, and with the high-pass filter, you get the edges. So let's look at what we get. Now the histogram has a completely different shape, and it's much more clear in this case if we have a background or if we have some characters or some text. So this is an easier case to segment than we had before. And looking at the ROC curve of this case, we can see that it's quite good improvement. We are getting closer. That is what we are aiming for in our segmentation. And now we can compare. And I more or less already gave the idea to this question, but so comparing the two histograms, this one is not going to perform so well because we have a large overlap between the two classes. Here we have much less overlap, and no. Let's go back again. And this is also what we see in the ROC curve with the area under the curve that increased. So last thing before the break is clustering, and that's now we are leaving those histogram-based methods. And clustering is a method that tries to bunch as many pixels together with more or less the same properties. And here we can have a lot of different feature vectors, and afterwards we have the classification where each group of pixels is labeled with some label. Let's start with some example data. We have here just some points in a two-dimensional space. So we have one group here, one group here, and if you look closely, it is probably rather two groups. So we have, in this case, we have actually three groups, and we want to separate them. And these dots here, you can see them in this case as a two-dimensional histogram, a bivariate histogram. And that is something you can use also with any number of dimensions. This clustering technique will find nice centroids of each cluster. So if we try running an algorithm called k-means, and we say we want two clusters, so that is actually, this is a function from scikit-learn called k-means. Here we initialize it with that we want to produce two clusters. And the next step is to give the data to this fitting and do fit predict. And that gives us our group, which then tells us we have some pixels are belonging to group 0 and the other ones are belonging to group 1. And it can be nicely colored, like you can see here. We have our two groups. So this is a win. Now we can look at what is this algorithm actually doing. It starts out with unclassified data. And unclassified data is then the next step is to initialize the classes, and that's done randomly. So you have an image where every pixel has a random class. It's just a snowstorm. And the next step is you take, for each class value, you compute the centroids or the average value, and that gives you a hint. Okay, I have a centroid probably in the beginning they're very close to each other, but you take always the closest class and reassign, and then you update this class map until stability. And in the end, you come out with this final segmentation or clustering, and you are done. And looking at the whole how k-means work on a different number of clusters, I played with clusters 2, 3, and 4, and I run the k-means with these number of clusters and do the prediction, and you can see with 2 groups, it makes sense. We have 2 clearly separated groups. 3 groups also kind of makes sense. 4 groups, yeah, then you can see that actually 4 groups is a little bit too much. And if I now would run this even with 5 groups, no, I shouldn't have done that. Okay, then I have to go back many steps. I think in this one. No, ugh, come on. This one. So, yes. So, now we can see. And now if I add the 5th group, then it starts doing strange separations in our data. And this is something you can use as a method to see how well the clustering is doing, and you can also do plots to see the performance and see when you do over-segmentation in your clustering. So, and then it's a question what kind of vector space we have. And we have different, we can have locations, we can have color intensities, also different orientations or shapes. You can add more or less everything into your classes, and it will, in the end, find centroids around clusters, unless they are completely homogeneous distributed. And here we can try with the cortex image, where we now have the possibility to play with the coordinates. So we give it a little bit spatial information. We can also play with a weighted neighborhood, or we can also look at edges. And all these can be plugged into the k-means, and it tries to find something. So here we have created a table where we have the x and y coordinates and the intensity. And if we try to run a clustering on this, it's not very convincing. The reason for this is that if you look at the values on the intensity and the values on the x and y coordinates, you can see that there is a large scaling difference. And that results in a dominance of the position compared to the intensity. So what we need to do is to divide our x and y coordinates by factor 10 maybe, and then it starts getting a little bit, a little bit better, but still not convincing to find the cortex, if you remember what the red area was looking like. And then we can do other things. We can also do the k-means clustering, yeah, as we said now on single images. We can do bimodal data, something actually I'm going to look into on lecture 10, I think, 9 or 10. where we have different modalities. Could be MRI and X-rays, could be ultrasound and MRI, or in my case, I'm working a lot with X-rays and neutrons together. And then we can do clustering based on these two. But the important thing is that the two modalities should have specific or characteristic features that the other one doesn't have. Otherwise, it doesn't make really sense. Hyperspectral data, that you can look into this example. That's a lecture I did on machine learning, and that specific example was about principal component analysis and then doing clustering. Oh, I'm running away in time. Let's take a break, and then we continue with quad trees after that.